What is swarm robotics? Swarm robotics is a collective of lots of robots working in unison to try and complete an overall task. Now, we all know what traditional farming is. Big tractors spraying far too many chemicals all over the environment. This is where the small robot company come in. Their plan is to use smaller robots to achieve the tasks required in farming on a plant-by-plant basis. This means instead of spraying large amounts of chemicals throughout the field, they deliver the appropriate amount to each individual plant that needs it. The principles of the small robot company are to increase yield while reducing cost, to reduce the negative effects on the environment, but while not putting anyone out of a job. Currently, they have one robot which goes around the entire field collecting data. After this, it returns to the base for this data to be processed. We think we could improve on this. We had three main requirements for our project. First, we needed somewhere to start. We decided to create a simulation to represent what the small robot company currently do. The next, we wanted to add communication. This would open up lots of options on how to improve the efficiency. Finally, we wanted to add multiple robots. We wanted to make them all work as a team. However, our main aim was to reduce the time, thus reducing the effects on the environment and reducing the cost. Therefore, reducing the cost to the small robot company, but also the customers. I will now hand over to Chris, who will talk more about the simulations.
The experiments were performed using Argos, which stands for Autonomous Robots Go Swarming. It is a multi-engine, multi-robot simulator which is used for simulating swarm robots. The simulator is fed a heat map which is displayed on the right. The attempted goal of the simulator is to recreate said heat map using the ground sensors that the epochs are equipped with. The ground sensors return a reading between 0 and 1, where 1 represents a black ground and 0 represents white ground. This information is passed on to MATLAB, which uses these values along with the X and Y coordinates to generate recreate the heat map. Here we can see the display window of Argos running the experiment for base simulation. This is replicating the current model that the small robot company had, by which the robot moves around the field taking sample readings, after it is done which it will return to the kennel. As you can see here, it is returned to the kennel, and now MATLAB will try to recreate the heat map displayed on the arena floor using the ground sensor readings and the X and Y coordinates. Obviously, this has been sped up. Normally the simulation would run a lot slower. This is extension 1. In this extension, we have added communication between the Tom robot and the data hub. This allows the MATLAB script to generate the map dynamically as the robot is still scanning the data. This allows a farmer who would potentially use this service to make decisions on their farm before the Tom robot had even completed its task. Another addition added to this extension was the inclusion of variable sample rates. This allows the Tom robot to increase their sample rate when they find a patch of good soil, or to reduce their sample rate when they find patches of bad soil. This is done because in the real world scenario, the Tom robot would be likely performing this job over a period of a long time. So minimising the number of scans that it has to waste will save the Tom robot a fair amount of energy, and as a result will save the farmer a fair amount of money. This is extension 2. For this extension, as you can see, there are multiple robots. The user can define the number of robots, but for this example we've only chosen 4. The robots will divide the field up amongst themselves and then choose an equally spaced segment of the field for them to scan. Once the final robot has finished the path, it will return back to the base. It also signals the other robots to immediately return to the base.
For the base simulation, we tested 2 different paths. The serpentine, which is the traditional path found in farming, and the sinusoidal path, which you saw in the simulation videos. This is the path that showed the better results. Here we can see a plot of the average distortion and simulation time for different scanning intervals, which is measured in simulation time steps. At scanning interval of 50, you can see the 2 trend lines crossing over. This we think will give the best balance for reducing distortion and the time taken to complete the simulation. Here we compare the base simulation with enhanced version 1. You can see from how the orange trend line is below the red that enhanced version 1 tends to have the lower distortion value. At scanning interval 50, the base simulation has a 3.6% lower average distortion than enhanced version 1, but it is 9.1% slower and has a higher range than enhanced version 1, meaning it is less reliable. Therefore enhanced version 1 we think is the better simulation. For enhanced version 2, we start to move on to multiple robots and look into how this affects the distortion and time of the simulations. The red shows the average distortion, while the orange shows the average simulation time. Although the trend lines cross over at 2 robots, we think 4 robots would be the better option, and we will use them for the next comparisons. This is because they have similar distortion values as for 2 robots, however the simulation time is a lot lower. This top graph shows the average simulation time for different simulation versions. Enhanced version 2 is 48% faster than the base simulation and 43% faster than enhanced version 1. The bottom graph shows the average distortion values. Although the base does have the better value, enhanced version 2 hasn't yet had the time to optimise the different scanning intervals, and future experiments may show that it has a lower distortion value than the base simulation does currently. All the experiments just spoken about were virtual experiments. Alex will now talk about progress made towards the physical simulations.
The use of physical robots allows us to move into the next step of our simulation. In this case, we're using epochs. The epochs, as you can see, have only 2 wheels. This means that they rock backwards and forwards as they move along. The sensors are at the front of the epoch, meaning that as they rock, there will be more or less light being allowed into the infrared sensors. This will give a data that is different than that from the virtual simulations. This is what the physical simulation looks like. As the robots move down and up the heat map, they'll produce data, but that data will have much more noise than usual. Once these simulations are performed and these problems are solved, more variables will be introduced, such as the lifetime of a battery, for example. This setup allows us to validate the experiments that we've made in simulation in real world. Once these systems have been developed to an optimum, then they can be implemented into the small robot company robots, which would in turn result in a more sustainable way of farming. With more interest and more funding into this technology, this has the potential to improve farming to a level where it is more sustainable for a better future.